scalability, flexibility, and the simplicity of the cloud. And that's pretty much what cloud native is. Now, in terms of cloud native, there are a number of factors that impact the cost of your cloud architecture, your cloud applications, your VMs, and everything, from the vendor to the location you pick and all of those. There are a number of factors that impact the cost. One of the core factors that impacts the cost of your cloud native workload is the machine architecture. What do I mean by the machine architecture? Everything revolves around the CPU of a machine, whether it's your phone, your laptop, your bread toaster, your fridge. Yeah, fridges these days. Fridges do have CPUs, right, Andrew?
Smart ones do, yeah. The ones with like Alexa integrated exactly. And things, yeah.
Yeah.
I imagine even the basic ones will have something in there as well, just to regulate the temperature.
Yeah. So everything has a CPU, and the CPU is essentially what carries out the tasks. Now, the CPU is instructed through what is called the instruction set architecture. This is how all the code and everything that we do is translated to instructions that the CPU can understand and then carry out our instructions for us. This instruction set architecture is broken down into two. We have the complex instruction set machine, computer, and then we have the RISC, which is the reduced instruction set computer. Let's talk about the first one. The complex instruction set computer is pretty much, as the name implies, it's complex, large, diverse set of instructions can be carried out over a given period of time. Let's just put it that way. So you have this complex instruction set. This complex, you can think of it as algorithm, or you can think of it as a language, or however, you can think of this conduit of taking whatever instruction we want to give to the CPU and translating it to a language that the CPU can understand. This particular instruction set architecture is that it's complex, it's big, it can do a lot of things over a given time. So, sorry, if it's 2 seconds, this complex instruction set can carry out a lot of tasks in terms of parallelization and everything you can think of, it can do with complexity. Now, those instruction sets is originally has been the fault of Intel. Intel's x86 architecture has always been the dominant, the pretty much standard for the complex instruction set computer. So nearly every computer before the recent years has been based on this architecture from Intel. There's also AMD, and AMD Advanced Micro Devices, they've also have their ISA architecture, or based on the ISA architecture, complex instruction set and computer architecture. They're also there, but they are not as big. Of course, AMD is also coming up with their Ryzen and EPYC server, CPU, and all of that. They're also coming up with that, but they are not as big as Intel. So in the entire CPU market, Intel is pretty much the dominant factor. But as with everything that is complex, the more complexity, naturally, the more cost. Why? Because of its complex nature, it consumes a lot of power. So Intel's CPUs generally consume a lot more power because they can do a lot more within a given set of constraints. So if you throw a given task at it, it can eat it up in a fraction of the time. And that translates to using a lot of power. And using a lot of power eventually comes down to a lot of cost. So naturally, Intel machines are, or Intel or complex instruction set-based machines have been expensive to run, whether locally or in the cloud. They've been expensive to run because naturally they are complex and they consume a lot of power. And as we all know, power is expensive. We can imagine the data centers, the amount of power they consume. All that cost has to be spread around the VMs and everything we spin up. So they get to be expensive. Now, like I said, there are two instruction set architectures. There is the complex instruction set, which is dominated by Intel and AMD to some extent. And then we have the RISC, which is the reduced instruction set computer. This is a much more simplified instruction set architecture that is able to carry out tasks at a much more efficient rate over a given period of time. So RISC is sort of not RISC as in RISC, R-I-S-K, RISC as in R-I-S-C, just to be clear, because unfortunately English, they sound the same. So reduced instruction set architecture or reduced instruction set computer instruction set architecture. We are developers, so we are used to this kind of tongue twisting words. So reduced instruction set computer architecture does the work at a much more efficient rate over a given period of time. So compared to the complex instruction set computer architecture, it can be argued that RISC has a much more performing advantage or performance advantage over RISC. But again, that comes at a cost. And then RISC is much more efficient in terms of power consumption because it does more or a little bit less given the same resources. So those translate to power efficiency. Now, the most popular RISC examples we know at the moment are the advanced RISC Machine architecture from ARM. So again, this word has been very confusing. You can call it ARM, you can call it ARM. I've heard people call it ARM, others call it ARM. However you're comfortable calling it, just, I don't know how, Andrew, how do you call it?
I normally say ARM, in contrast to how I do normally spell out all initialisms. Like, it's always been SQL for me, but I know a lot of people say SQL. But in this one case, exactly. I do say SQL. ARM.
Yeah, really. So we have advanced RISC machines, which is an implementation of the reduced instruction set computer architecture. Originally, it was actually called Archon RISC Machine, but changed to the advanced RISC machines. Now, other than the cost, the lower power consumption, the most significant impact of the ARM architecture and its popularity in recent years has been single-handedly the licensing model. Now, if we step a little bit back up here, both Intel and AMD have the intellectual property for the complex instruction set computer, and then they create their own chipset. So Intel actually manufactures chipset based on the complex instruction set computer instruction set architecture. Now, ARM has the intellectual property to the ARM architecture, but ARM does not manufacture chipset. This is a very important distinction. So ARM has this intellectual property of how to manufacture a chipset based on the RISC architecture. You can think of it as a blueprint. So you want to build a chipset or a CPU based on the reduced instruction set architecture. ARM has the blueprint and everything, but ARM itself doesn't manufacture the chipset. All they do is license the intellectual property, and then you can just go out there and do whatever the flying interest you want to do. You can just go out there and then do it. So this is a very important distinction. Right off the bat, from an economic perspective, it means that ARM has a lower overhead cost than Intel because they don't have all the manufacturing overhead there, the R&D and everything that needs to go into manufacturing the literal physical manufacture of the chipset. ARM doesn't have that overhead. Intel has that overhead. AMD does have that overhead because they actually do manufacture. So they hold the intellectual property and they do the manufacturing. ARM has the intellectual property and they just do the licensing. So anybody can go and license the ARM architecture IP and then manufacture their own chipset based on the architecture. And this is a very important distinction why right off the bat, apart from the energy efficiency of the ARM architecture, it's also relatively cheaper to manufacture because, of course, there is the economies of scale. These guys can simply scale out to different manufacturers, but Intel has to do it themselves, do everything in-house. So there is that factor. And so this is pretty much like the Jakarta EE standard, where all of us go in and then come up with a standard. So Jakarta EE 10 standard is made up of this and that and that and that and that. And then you have the actual implementations of the standard, like Payara server and the others out there. These are the actual implementations. It's the same. There are many implementations of the ARM architecture out there. So when you hear the ARM architecture or you hear an ARM server or whatever, just think of it as a custom chipset based on a license or the licensed IP from ARM. And this is a very important distinction that makes it right off the bat ARM be much more efficient, much more economical than Intel. Now, historically, ARM has been targeted at low power devices because, of course, it's power efficient. So things like your phone, your laptop, your tablet, these guys are low power because they mostly run on batteries, and then you charge them, then they go back to running on the batteries. So they need power efficient chipsets to do the work. If you put Intel into a mobile phone, that would be a problem. You have to connect your charger to the phone and roaming around the house. And then we are back to the old days of wire connected phones and all that. So these devices, because they are said to be low powered, they need to have a chipset that is much more power efficient. And ARM has been the de facto standard or the de facto implementation chipset in that sphere for a long time. But in the last few years, ARM has made incredible inroads into the server market. Now, we can argue that one of the things that has made ARM very, very, very popular in the last few years has been Apple's chipset, Apple's M1 based M1, M2, M3 chipset. These chipsets came, and then the incredible battery performance that people were realizing got people turning their heads. Whoa, okay, so it could be this good. And then since that time, there's been a lot of resurgence of ARM in the server space. It used to be there, but it wasn't this popular. So now ARM is now getting very, very popular in the server space. Now, if you have Amazon creating an implementation of the ARM architecture in the Graviton chipset that they offer on their AWS EC2 instances, then you need to pay attention. So an example of the implementation of the RISC architecture based on ARM from Amazon is the Graviton CPU architecture machines they offer. So if you go to AWS now and you want to spin up a machine, you have Intel or x86 based machines, and then you have the ARM architecture machines that you can spin up. And if you do a price comparison, you will see that immediately they are very, very, there's a difference in the price because naturally the ARM architecture is economically cheaper than the Intel machines. So you have that. And then there's also Google Ampere Ultra, which they call Tau or Tor or Tau. I don't know how they choose to call it, but it's TAU. Andrew, how would you call it?
If I was to read that, I would say Tau. But as I say, I don't know. Google do tend to say things not necessarily how they would normally.
Yeah. Okay. So there is the Tau from Google, which is also based on the on the RISC architecture. Yeah. So now all of these big players, and you have independent cloud providers, nearly all of them now offer ARM machines, which are very, very cheap. Now, tying all these in, what does it mean for you as a Jakarta EE developer? Again, as I started the preamble, all of us want to see, of course, whether it's buying spaghetti from the from the shop, from Lidl or Aldi or wherever, or spinning up a VM. We all look at the price and do a lot of calculations. So what does it mean for you as a Jakarta EE developer? We can open up this particular link here. I can copy this, go back here and copy this link here. And then we can just do a simple quick look and then hand over to Andrew to demo this for us. We can go here and paste this guy in here. Now, this is a website that shows nearly all the things that Amazon offers, or all the popular things that they offer, and their pricing and everything. Now, this is the EC2. If we come here, they offer the Graviton implementation of their VMs under the they call it T4G. So if I type G in here, they should give me all the Graviton-based, so the G stands for Graviton, Graviton-based the VMs that they have. Now, if you look here for this particular nano Graviton machine here, for the smallest, the lowest, for 0.5 gigs of memory, and then 2 virtual CPUs, blah, blah, blah. We have, for the reserved instance, we have the price being 0.0026. We scroll a little to the right, and then we have the spot minimum cost here being 0.0020 hourly. Now, if we go back and then look at the normal nano here, you can see for the same machine here, there is this guy here. What's this? Are we on the same machine? Are we? Yeah, this one. Yeah, this one. So there is this guy. Yes, T3 nano, this one. There is 0.0033. And then for the spot, you have this. So if you are reserving here, there is a price difference, and then on the spot, there is. So if you walk through this particular list here, or this particular site here, you do the price comparison, you will see there is the app architecture pricing is almost always different in terms of the variety. It's different. It's a little cheaper than the Intel machines. And what that means for you as a Jakarta EE developer is that when you develop your application, naturally you want to put it in the cloud. Even if it's an internal application, it will still have to be on the cloud somewhere for it to be accessed internally or however. Nearly everything is done on the cloud. It means that you want to have your runtime support the ARM architecture so you can take advantage of the cost savings that comes with ARM. In the past, Payara used to have support for the x86 architecture. And then about a month, I think 2 or 3 months ago, we also introduced the ARM support for our Docker images, which means that now you can take advantage of all the cost savings that comes with the ARM CPU architecture. And this is very important because the cost savings that the cloud providers realize now becomes something that you as a developer can also tap into just by switching the architecture. You don't need to change your code or anything. You will just have to switch your architecture based on the VM that you pick. And then you can tap into this cost savings. So let me leave you with Andrew here to show you what I mean by Payara's Docker image support for the ARM architecture. Over to you, Andrew.
Yeah.
I'll stop sharing my screen.
As Lukman said, I think it was around February or March, sometime around then. Time marches on, so it probably is more like 5 or 6 months now. Our Docker images were very much just tied to x86, and if you try to run them on if you try to run that Docker image on an ARM machine, there was a high chance that you would actually just hit an error. Particularly if you try to build it, because it tries to install some things during the, I think it tries to do some signature validation, and it was specifically trying to validate against the x86 signature rather than validating against your operating system specific one. So while obviously Java is always been compile once, run anywhere, as the tagline goes, or something to that effect. I'm fairly certain that's the one. From a proper quote unquote VM standpoint, you could spin up an ARM instance and run Payara server or Payara micro on that instance without any issue. The Docker side of things was always a little bit more restrictive. That, as of February, March time, is now different. So there isn't too much to show because, as I like to say, it just works. As Todd Howard also likes to say, it just works. Except hopefully it shouldn't explode like most of Todd Howard's things. So the sharing of the screen. Select window or screen. I'm just going to share the screen because it's a bit easier from that perspective. So hopefully everybody can see my screen. Please scream if you can't. But this is the output of a... I'll make it even bigger for those who wear big, thick glasses like me. This is from the latest one, or we're actually just in the midst of the release cycle for the 6.2024.7 release, but this is the latest as of released one as of now. This is just what I've pulled from there, from the Docker Hub. And if you look closely through the JSON, you'll see something along the lines of operating system, Linux, architecture, AMD 64. This is what you had before, but if we again go to Docker Hub itself, it's over in this tab. Let me pull it over. There we go. We now make use of the multi-platform builds. So this should just work. So for each tag that you see, you'll actually see these two different options, and if you click into them, you'll also have the ability to switch between them. And for those particularly sharp-eyed, the SHA digest changes. Sorry, zoom again. So the SHA digest is different between them. So there's AMD and ARM 64. So as said, this should just work. Obviously, I'm on a Windows machine here, but with one of the recent Docker API updates, that's all the wrong commands, Docker pull, they added this platform option. This is obviously only useful if you're actually on something which supports multi-platform images natively. If you are actually just on an ARM machine, you don't have to do anything. When you just do Docker pull or Docker from, thankfully, it will just figure it out for you. Your Docker client knows if it's on an ARM machine or if it's on an x86 machine, and it will just pull the correct image. But if for whatever reason, such as for a demo, thank you, Docker, you can actually explicitly say, I want the AMD 64 version. And obviously, I've already pulled it, so hopefully it shouldn't actually have to download anything. But when I now do Docker inspect, hopefully the architecture is now different. Oh, wait, no. Why didn't you change? Did I do it wrong? Ah, yes, I did. I typed AMD. ARM 64, please. ARM 64, thank you. Oh, God, I thought the demo drama of, oh, it's gone wrong. Thankfully, no, it hasn't gone wrong. So I won't be able to run that locally because, as I said, I am on Windows. But you can explicitly force it if you absolutely require. So just to reiterate, you do not have to do that if you want ARM images. If you are running an ARM machine, an ARM VM or an ARM container, it will just auto-magically figure that self out for you. You don't have to do that. And the same thing can be done with the from when you're creating your Docker image files. You can do the same thing can be done there. You would just type in your from, you would just specify ARM64 or AMD64, whichever you so desire. Alternatively, just leave it there and it will figure it out based on what you are running on. So in the case of building those images, for those of you who are watching things, you will have probably noticed some of the image layers changed when we introduced this. This is because we, as a part of this multi-platform build, we had to relayer how certain things are done because internally we use BuildX, which is actually built into, at the very least, Docker for Windows. It should probably be there on most Linux Docker clients, but obviously your mileage may vary depending if you're running on some obscure Linux distro or some cut down version for servers. But BuildX is built into Docker for Windows at the very least, and most Docker clients. And this is something that you can use to actually generate multi-platform images yourself, and something we make use of. The downside of it is that when you try to chain images, which is what we were originally doing to keep the image layers a bit smaller, you can't do that locally. It is one of the big downsides we came across of unless you publish those intermediate beginning layers. We used to have a layer called Payara base, I believe it was called. Unless you publish those, you can't make use of it. So if you were actually copy pasting from our Docker image file or adjusting it in some capacity, you may notice some differences and may have to adjust for that. Even if you are building from it, you may also notice some differences if your local Docker client. So if your local Docker client didn't actually support BuildX and you were copy pasting from us and suddenly you started getting errors, that'll be why. Just as an aside, the way to get around that, if you're building with us, is to set that to nothing. So just set the system property of Docker.platforms to nothing, because by default we do utilize BuildX, but if you override our default values and set the Docker platforms to nothing, it will use the inbuilt cloud. That's just an aside for those of you who are building based on our own source code.
There's a question.
Yep. Oh, questions. Works for ARM64, ARM7 as well. My knowledge of ARM of the versioning of ARM is probably not what it should be, but I believe it should work on both because ARM64, I believe 64, I think is just the bit size. You get both ARM7 and ARM8 with 64. But again, I am not an ARM spokesperson. I'm not particularly massively up to date. I haven't memorized their versioning, but it should work on both because it's just ARM64. This is one of the unfortunate things of when you, or one of the reasons why ARM has typically been a bit slow on the uptake in comparison to x86 is because of that backwards incompatibility. Of x86 has historically been very good for backwards compatibility. ARM has been a bit more happy to just drop certain things. They've said they've promised they're going to get better at doing that now, but I believe in this case it should work for both. I do not have instances off to hand to test it. I'm not even sure what the default on AWS is, if it would be ARM7 or ARM8. I would assume
it's 64. The 7 is the older 32-bit version of that architecture. So in
I
this
thought
case,
they're both 64.
Docker, so if it's Docker, then if you have Docker running, which I doubt, on the ARM 32-bit, then you should be able to, wait 1 second. This is 64-bit, so no, this should not even work on it because this is 64-bit. The Docker image is 64-bit. So this should work on the ARM64 and not ARM7. And ARM7, I don't even know any modern device that runs ARM7 because they are very old, very uncompetitive version of the architecture. Nearly everything now in the last, 5-10 years is based on ARM64. So if you are spinning up a server, you are going to get ARM64 by default. And that is it. If you have Docker running on an ARM7 device, then in theory, you should be able to get it to work. But that will be a lot more hassle than than anything else. So you should just stick to ARM64 pretty much. ARM7 is a 32-bit older generation version of the architecture. Yeah. Okay, David, hopefully that answered your question.
Yes, apologies for my misinformation at the start.
Oh, that's fine. The whole ARM stuff has always been, it's part of why it's been a little bit unpopular, because it's been a little confusing and all of that. But hopefully, after our glorious Apple Inc. Paved the way with their M1 chips, M1, M2, and I think it's now M3 or M4 chipsets. Now they're all going up and everything is following suit. So David, and for the record, nearly everything else is 64-bit for ARM, and that should be able to run nearly anything out there for your purposes. So tying everything back in again, for you as a Jakarta EE developer on the Payara platform, now you can take advantage of these cloud savings that come with the ARM platform to optimize your cloud cost, because again, we are all interested in cloud saving. And this is one of the ways that for us here in Payara, we help you save cost, is to look around what is saving costs for people in the cloud. And then we go to the technical drawing board and try to implement that so that you can have something to save you cost. Because in the end, that has always been the force of Jakarta EE, as simple as you can get it, straight to the point. And Jakarta EE somehow is similar to the ARM architecture anyway. ARM has the IP, licenses it out for people to implement. Jakarta EE is the standard. And then you have different implementations like Payara and all the others out there. So they are pretty much cousins, if you so will, in terms of how they work. And this is our way of helping you save costs in the cloud, because things are getting quite expensive in the cloud. So any cost savings,
they like to lure you in, going, look, it's only part of part of a cent per minute. It's like, yeah, but that adds up quickly.
Yeah.
But this is something I also wanted to touch on. Obviously, your mileage may vary. There is never ever any silver bullet to performance, but a lot of things do indicate that ARM is generally better, particularly in the cloud, where, as Lukman said, efficiency essentially, or the efficiency of the chip essentially relates to cost. At least for now, where their price, Amazon and Microsoft are charging less for their AMD chips. They're not price gouging you quite yet, but one of the advantages and one of the reasons why we went for this BuildX solution of having the multi-platform images, so rather than having a dedicated ARM image and then a separate dedicated x86 image, is to actually help with that kind of performance testing and to help with that migration. In the spirit, once again, if compile once, run anywhere, you should just have to rebuild the Docker image. That's it. It's essentially just rebuild the Docker image for that thing and publish it. And assuming you're also using BuildX, you can then very easily have a multi-platform image of your own and compare between the ARM machines and the x86 machines, because you don't need to actually edit your Docker image at all. You just need to build it for the multi-platform, and then Docker auto-magically will pull down the correct platform for you.
Yeah. So again, it's important, like Andrew said, for the record, when we are talking about efficiency, we are talking about the cost savings that you save. We are not saying ARM is necessarily slower or faster than Intel. That is up to you to measure. That is up to you to find out, because these kind of benchmarks are almost always relative and subjective. So there is no universal answer to that. One of the fastest supercomputers in the world runs ARM. Another fastest supercomputer runs Intel. So we really can't say which is which. In terms of efficiency, and meeting you halfway from Payara's perspective is to just help you take advantage of the cost savings that let these cloud providers get, that they pass on to you in terms of relatively cheaper instance cost. And that is what we are trying to help you take advantage of. So tying everything together and wrapping up, in the absence of any question, cloud native Payara or Jakarta EE essentially anything that helps you take advantage of the cloud. And one of the core aspects of the cloud is the cost and cost savings. And what is cloud native? Again, that is just it. And the factors that impact cloud native, one of them is the cost of the architecture that you are running. We said there are two architectures out there. We have the CISC and then we have the RISC, RISC architectures. Intel has always been the master of the x86 architecture, which is the complex instruction set architecture. It's large, it's diverse, can do a lot of things, but can also consume a lot of power. And with more power comes more cost. So there is the reduced instruction set, which is ARM. The popular implementation of that is ARM, and ARM is essentially advanced RISC machines. Or the intellectual property for that belongs to ARM Inc., which we said has the intellectual property but does not physically manufacture the chips like Intel and AMD do. So they license it, so nearly anybody who has the pocket can go license it and then manufacture their own chipsets. There is Amazon Graviton, there is Google Ampere Ultra, and there are others out there, Alibaba and all those.
Snapdragon,
Yeah, exactly. Snapdragon, all these ones, they are all implementations of the ARM intellectual property, the ARM architecture. They are all implementations of that. And for you as a Jakarta EE developer, it means now you have the option when you are containerizing your applications. Payara has this ARM image that Docker, like Andrew demoed, will automatically figure out what platform you are on and then drag it for you, pull in the image, the necessary image for you. So if you know Payara does this for you, Payara has the ARM image. You just pin up an ARM image on your cloud provider, do your Docker, blah, blah, package everything, and then pull it in and take advantage of the cost savings. So this is one of the ways that for us here at Payara, we help you take advantage of the cloud native nature of the current cloud infrastructure that we have out there. You take advantage of the cost to save some money, because we believe our customers saving money will eventually be us also saving money. So the more money you have, the more it will be available for you to expand your offerings to your customers and everything, and the better and happy everybody becomes. So we believe in offering you all these options that you can take advantage of in this cloud native era. So in the absence of any questions, I'll give Andrew the last say, and then he can hand over to our host, our co-host, Kiara, who is here. We started with Dominica, but Kiara is here now to take over from her. Yeah, so over to you, Andrew, for the last one.
Yeah, so for the last bit, I was just going to mention or briefly gloss over, because obviously it's all going to be dependent on your exact scenario and environment, but some very quick best practices of for example, we always will say that the Docker images that we provide are not necessarily, once again, they're not the silver bullet. They're essentially examples, and that they're good to go if you for development and testing and even for prod in certain circumstances, but it's not going to be fit for prod in every single circumstances. For example, the images by default will make use of absolutely all system resources available, because the images themselves are not constrained. So you, for whatever reason, in your production environment or your testing environment, might want to constrain the image to one CPU or something to that effect. But then also just the configuration of the images of or the containers even, because images are not immutable. But for the actual configuration of the images, don't abuse the post-boot scripts or the configure or the immutability of the server itself. So this is getting into where that distinction between Docker containers, while are similar to VMs, are not VMs, and they shouldn't be used in exactly the same way as a full proper virtual machine. They are meant to be packaged containers which you just push with minimal config, preferably with no specific config outside of environment stuff. So don't abuse the post-boot scripts. This is particularly true for deployment of, if you're always going to be deploying the same thing and this is generally actually true for Docker images anyway, you should be ideally rebuilding the Docker image. It is very easy to just do it from Payara server and then deploy the application and then build that as an image, and there you go. And because one of the reasons you want to be rebuilding those images constantly is because Docker tags they're not like version control tags. They change. Docker tags themselves are mutable. Whenever you're pulling in the latest tag is the easiest way of showing that example of the latest tag changes constantly. It is essentially the very latest build and published version of it. This is also true for the versioned ones. So for in our case, for our Docker images, we version them based on the Payara version bundled in, but we have a different one for each. We have a different tag for each one. But we also pull from the Azul JDK image, which comes from a Linux distribution. You want to be constantly rebuilding these because you want to be getting the updates to those images. With our images, we frequently update them for the latest version of Java, but the Payara version on it stays the same. So you want to be rebuilding those. You don't necessarily just want to have a single container and then constantly, every single time you start it, load up the admin console and start configuring the server or something like that. No, you should ideally be trying to have it configured in the actual image that you're using. While obviously you, from a development point of view, it is handy to be able to just constantly redeploy to the same server without having to rebuild the image and things. This is that convenience versus performance aspect of you shouldn't, when you get moving towards the production side of things, you shouldn't be deploying or redeploying to the same image. You should be actually creating a new thing, a new imaging container. And we provide tools to help with these with the actual warming up of it. Of obviously, when you're completely starting from brand scratch and reconfiguring it, the server has to start up, do all that configuration that you're supplying via the admin console or a postboot script or something to that effect, and then deploy the application, which involves unpacking the application and then loading it up and registering it to the server. There are ways. This is one of the reasons why we have these options, such as the warm-up option, which will load the application server, apply all the config changes that you require, deploy the application, unpack it, register it, and then shut down. And then you can use that as a part of your Docker image, because you can include that in the build of your Docker image. And then when you get to creating a container, it's good to go outside of supplying any extra environment-specific details. But the actual application is already registered, which is where you get things such as microprofile config, and the other dynamic configuration mechanisms. Make use of these. Microprofile was built around the use of microservices, and microservices were very heavily lit, or they very nicely fit into that cloud landscape of being able to just kill them, start them back up. That kind of flexibility, not just having the big monolith, which it's just like, oh god, it's down, now it takes 10 minutes to come back up. Where's my notes? I've lost all of them. So yes, and then my mug, as humorous as it is, it's not just for show. Size does matter. When you're from a deployment standpoint, don't have absolutely everything. While it's nice to have a bit of everything and absolutely the entire server available, we do have Payara Micro. Payara Micro is the more microservice-focused solution, and it is the more Docker-focused solution. And if you don't absolutely need the full Jakarta EE platform and all of the other things that the server has on top of Micro, why are you using server? Is it just because you're used to it? Times change. Change is sometimes scary, but Payara Micro is, if you don't need that full Jakarta EE platform, Payara Micro is a lot smaller. It's a lot quicker to start, and as has been said, efficiency equals money. So you want to have those things there. So size does matter. And while sometimes money is of no object, sometimes it is when you're getting given $5,000 AWS bills because you've accidentally left something running, burning CPU in the background. Yeah, and so that's kind of my very brief gloss over of deployment practices. So I will now open it up for questions and any final comments, and to whoever wants to actually close this out. You can tell we practiced this.
Thank you, Andrew. For anyone listening, remember you can either drop your questions in the chat or in the Q&A function, and we'll read them out and give you answer live. If by any chance we don't have time to cover your questions today, don't worry, we're going to answer to you later on.
Yeah. Okay, so that is it from the chief chef in the Payara engineering kitchen. Andrew has given you all these tips, so you want to take note of them, because sometimes we tend to overcomplicate things that can be very simplified, and they are all part of the efficiency and cost savings. So like you said, if you can use Payara Micro in a smaller footprint image, why do you go for the whole tank when you could just use a pixel? So pretty much that is it is described. You want to take note of it. And I think this session will also be recorded and available on demand. So even if you missed it or you want to recap what he said, you can always go back to it. I think in the absence of any question, there is 10 minutes to the top of the hour. I'll hand over to Kiara to close the session for us, so we can all get some few minutes back to probably visit the loo or something and continue with the rest of our day. So over to you, Kiara.
Yeah, right. Thank you so much, Lukman and Andrew, for leading this webinar. And thank you for all the attendees. I hope you had a good time and you learned something new. Remember that if you want to test, for example, Payara Cloud, you can download, you can get your free trial from our website and register for free. Having said that, thank you all for your time, for your expertise, and looking forward to the next seminar. So stay tuned to learn what's coming soon.
Okay, thank you. See you. Bye.